When the forces of nature are released explosively, the results can be devastating. And yet, if the current scientific picture is correct, nature itself got started in a kind of explosion. Billions of years ago, they say, the whole universe of space and time burst suddenly into existence. The fiery birth of the cosmos has become known as the Big Bang. But the more we learn about this singular event, the less it resembles any kind of explosion we've ever seen. Now it appears that the Big Bang is actually still underway, and it's picking up speed. In this episode, we'll hear from some of the world's leading cosmologists as they try to make sense of the Big Bang and its aftermath. The scientists who study the biggest subjects of all are the cosmologists. Armed with the laws of physics, an assortment of telescopes, and boundless curiosity, they've put together a picture of the universe that's strange, to say the least. And for the most part, they seem to enjoy their work.
Well, cosmology is the study of the structure and evolution of the universe as a whole. How did galaxies form? How did they cluster together? How did stars form within galaxies, and how did the whole thing evolve? So really, cosmology is a study of our basic origins. I mean, just like we want to study how cells formed on Earth, so too we want to understand how all the material of the universe came into existence and gathered together in clumps and galaxies and stars and planets. So it's a fantastic field. It's just one of the most thought-provoking fields that I can think of.
Cosmology has really made rapid progress in the last 10 years. Now, part of the reason for that is because 10 years ago we were so ignorant. And when you're very ignorant, it's very easy to make rapid progress. And we have made rapid progress in cosmology, certainly in the last 10 years, just because all of these new observations have come available.
The most notable recent advance in cosmology came about partly as a result of a survey conducted by Alex Filippenko and his colleagues from the University of California at Berkeley. They wanted to check up on the cosmic expansion to see if it was running at a steady rate. Back in the early 1990s, it seemed reasonable to expect that the universal expansion was slowing down. As Dr. Filippenko explains, it's all a matter of gravity.
After all, if you throw an apple in the air like this, on its upward journey, it's slowing down with time because the gravity of the Earth is pulling down on the apple. And eventually, of course, the apple even falls down because the gravity is so strong. Even if I were to heave this apple at a speed greater than the escape speed from Earth so that it would forever go away, it would still always forever slow down because the gravitational attraction of the Earth on the apple never stops. So we expected the attraction of all galaxies for other galaxies in the universe to be gradually slowing down the expansion of the universe.
To learn how much the universe was slowing down, Filippenko's team went looking for supernovas. It turns out there's a kind of exploding star that's enormously helpful to cosmologists. They're called supernovas, and they can shine more brightly than 1 billion suns. This makes them easy to see, even from halfway across the universe. More importantly, one particular type of supernova, known to the experts as Type 1a, always seems to have exactly the same brightness. In that sense, Type 1a supernovas are like the 100-watt light bulbs of space. A kind of standard light source so bright that one could vaporize an entire planet. If astronomers see the characteristic pattern of flaring and fading that gives away a Type 1a supernova, they know just how bright an explosion they're witnessing. By comparing that brightness to the apparent brightness, the amount of light they actually measure at the telescope, they can easily calculate how far away the supernova must be. Measuring distances in deep space is one of the greatest challenges in astronomy. So a star that reveals its distance like this is a thing worth searching for.
So we were finding these distant supernovae and studying them with the biggest telescopes in the world, and we were astonished to see that they were dimmer than expected. They seemed fainter than we expected them to be. And we interpreted this as being due to extra distance. So they were farther away than we expected them to be. And that means that the universe couldn't have been slowing down in its expansion, because then the things wouldn't have gotten so far away. In fact, it couldn't even have been expanding at a constant speed, because again, the supernovae that we were finding couldn't have gotten that far away in the amount of time the universe has existed if they had always been going at the same speed. So we deduced that in fact they must have been speeding up with time. That is, the universe is accelerating with time rather than decelerating as had been expected.
The astronomers were flabbergasted. When they get results the opposite of what they expect, scientists' first assumption is that some part of the experiment has gone wrong. Measuring the brightness of extremely faint objects is no easy task, even with enormous telescopes. Any number of factors can throw off the measurement. Was the power supply steady? Were the optics properly aligned? Had they been misled by atmospheric conditions, haze or smoke, perhaps, that had gone unnoticed at the time?
But we checked and rechecked both our observations and our calculations, and the answers simply wouldn't go away. The distant supernovae were too dim, too distant, and hence farther away than expected, and hence they were accelerating with time.
Pity the poor cosmologists. They had spent most of the 20th century coming to terms with the cosmic expansion. Now, it seems to be even weirder than they had imagined. Any explosions we know about slow down with the passage of time. The energy dissipates. The motions become increasingly subdued. But apparently, on the grandest scale of all, the universe itself, it's the other way around. The galaxies are flying apart from each other faster and faster as time goes on. But one group of astronomers was happy to learn that the universe is accelerating. The folks who measure the ages of stars had been trying to resolve a paradox. Measurements taken using the Hubble Space Telescope had pinned down the expansion rate of the universe to within something like 10%. Plugging that rate into a rather simple formula gives you the age of the universe, and it works out to be about 9 billion years. For most of us, that's an impressively long time. It's twice the age of the Earth, for example. But to astronomers, it seemed alarmingly short. They were convinced that certain stars were older than that by several billion years, or several gigayears, as cosmologists like to say. You can't very well have stars that are 12 gigayears old if the universe has only existed for 9 gigayears. Either the ages of the stars or the age of the universe had to be seriously wrong. The data from the Space Telescope seemed impressive, but astronomers were confident that they'd got the ages of the stars right too.
There's a really reliable way to measure the ages, and the physics that gives rise to the measurement is pretty straightforward. It's just burning of nuclear fuel, and we know how to do that to make power. So it's the sort of physics that people do in industrial facilities, let alone physics labs. So the process is extremely well understood, and it gives ages for the oldest stars that are at least 12 gigayears. So it doesn't make sense that the oldest things in the universe are older than the universe.
But if it's true that the expansion of space is accelerating, then astronomers had been using the wrong formula to calculate the age of the universe. Acceleration would extend the cosmic age enough to account for the oldest stars with a comfortable margin of safety. The New figures indicate the universe is about 14 or 15 gigayears old. So the accelerating universe helped to solve a paradox, but it still seemed a strange concept to many astronomers. Sometimes in science, a result as unexpected, as unorthodox as this gets put on the shelf and ignored for a few years in hopes that it'll go away. But as we'll see, a completely different group of scientists pursuing a different line of research has come up with new evidence that the growth of space is speeding up. Whether we like it or not, it seems there's a phantom foot pressing down on the cosmic accelerator. What is the current picture of the universe on the largest scale? We think it looks something like this. But don't be misled. We don't mean to suggest that the universe is shaped like your TV screen. It probably isn't meaningful to speak of the universe as having a shape at all. That would imply that you could somehow step outside the universe and view it from a distance. And don't ask what's beyond the borders of the screen either, because nobody knows. We can't say anything about the size of the universe except that it's huge. It might even be infinite for all we know. There's a limit to just how far we can see, and the universe seems to be fully populated with galaxies right up to that limit, and perhaps far beyond. But we believe that the universe has a pattern or a texture that would look about the same from any location. It's a texture rather like a sponge or the inside of a loaf of bread. Thin walls of material enclosing a huge number of bubbles or voids. Of course, the material that separates those bubbles isn't bread dough. It's made of galaxies, stars, and planets, plus a huge amount of mysterious dark matter. Stuff that we know is there because its gravity affects the things we can see, but that doesn't shine with any kind of radiation we can detect. And, of course, the whole thing is in motion.
The funny thing about cosmology, it teaches us, as we would expect it to teach us, how strange the universe is. And we'd expect it to be strange in the sense that our intuition, our expectations, are founded on a very limited set of circumstances in a very strange and special part of the cosmos, a small rocky object, not really like the cosmos in general, though derived from it. So anything you found out is almost certainly likely to knock your socks off. When Edwin Hubble found the universe is expanding, why, that was rather weird and strange.
The expansion that Hubble discovered is rather like the rising of a loaf of bread. The bread part, the cosmic dough if you like, doesn't actually get bigger. It's the bubbles that expand. Of course, in the cosmos, those aren't gas bubbles. They're empty spaces or voids. The expansion force seems to be a property of empty space, and it's actually inhibited by the presence of material objects. So, the galaxies aren't expanding. Our solar system isn't getting any larger. It's the spaces between the galaxies that are expanding. The emptiest parts of the universe, it seems, are swelling up. There's one more comparison we can make between the universe and a loaf of bread. Whatever sort of shape the cosmic loaf might have, it certainly isn't plain white bread.
And the fact is, the universe is about as complicated as it could be. We probably have dark matter that is both baryons, neutrons and protons, the stuff we're made of, and non-baryonic dark matter, you know, some exotic thing that we particle physicists talk about as if they know what it is, but they haven't seen it. And then, in addition to that, we have the most complicated, rich, interesting, Baroque sort of universe you can imagine. We have something that also has this big component of vacuum energy, or at least that's the way it looks based on the supernova data. So I think what it tells you is the aesthetic approach, the simplest thing that you can think of, is not always a guide to the truth. Sometimes you just have to go look, and you discover that the universe is actually much richer and more complicated than your imagination. In fact, it's always more complicated than you imagine.
Our understanding of the cosmic expansion has undergone a change in recent years. Cosmologists see it as a kind of struggle between two almost balanced forces. Gravity tries to pull everything together, while the cosmic repulsion force attempts to blow everything apart. There's evidence that once, for a tiny fraction of a second near the very beginning, the repulsive force almost got the upper hand. The universe expanded enormously, then gravity kicked in and almost stopped the expansion in its tracks. It's been slowly picking up speed ever since. Among cosmologists, this scenario is known as the inflationary universe. It was devised in the late 1970s, primarily by Alan Guth of MIT. Inflation theory explained a number of cosmic puzzles, and it made a big hit with the cosmological community. The splash even caught the attention of the popular media, though not all the reporting was accurate. Some headlines claimed that a new breakthrough had disproved the Big Bang.
Sometimes these headlines are a bit too terse. What they really mean is that we now have a modified version of the Big Bang, a more mature version, a better version. So it's not that the universe didn't begin with a hot compressed state, as the Big Bang theory had been saying for decades. It did. It's just that now we have a modification. Before the inflationary theory of the universe, we had no reason for the Big Bang. We had no reason for why the universe should be expanding. Now we have a reason. Given the creation of the universe and given an inflationary epoch, that naturally produces an expansion which later gives rise to the expansion that we see.
The universe began hot and dense. It started out so terribly crowded, in fact, that all the matter and energy were compressed into a sort of plasma that was almost featureless. But it wasn't perfectly featureless. It was riddled with random fluctuations that made the density vary from place to place by the tiniest amount. Those small variations would grow over time. Eventually, the denser parts became galaxies and clusters of galaxies. The less dense regions became those cosmic voids whose growth drives the expansion of the universe. In the early days, before the voids got too large, the material parts of the cosmos, the galaxies, stars, planets, and so on, were much closer together. Their mutual gravitational attraction acted like a brake to slow down the expansion. But it appears that the cosmic brakes are wearing out. As the distance between any two galaxies increases, the gravitational attraction between them grows less. But the tendency of empty space to get bigger remains the same. So, slowly, relentlessly, gravity is losing out. The expansion is picking up speed. It's a sign of just how new this line of research is that the cosmic repulsion force has a variety of names. The experts haven't agreed what to call it yet. It's a point of lively debate at scientific meetings. Some call it the vacuum energy or the false vacuum energy. To others, it's the cosmological constant. An increasing number of scientists simply call it dark energy. Whatever it's called, it has a profound impact on the eventual fate of the universe.
If dark energy proves to exist in roughly the amounts that the observations imply, then the future of the universe is utterly assured. It will never start contracting. Instead, it will expand forever, and it will accelerate its expansion, so it will expand faster and faster and faster until within a few 100 billion years, there'll essentially be nothing anywhere. Everything will be so far apart from everything else, and everything will have burned out in terms of stars, that the universe will be cold, dark, and empty. And for some people, it's a terrifying thought.
But the dissolution of the universe will never be a problem for people, of course. In a few 100 billion years, the sun will have long since flared up and faded out. The Earth, if it exists at all, will be a burned-out, frozen relic. There will be no humans around to witness the stars going out and the galaxies rushing away. And that may be just as well. Any intelligent being still left in that far distant era would face pretty discouraging prospects, especially if they were stargazers.
And indeed, the far future of the universe, from an astronomical point of view, is actually quite bleak, because what's going to happen is the universe's expansion is going to continue to accelerate, and all galaxies not gravitationally bound to the Milky Way are going to slip out of sight, because so much new space is going to be born in between those distant galaxies and us that their light is no longer going to be able to reach us.
100 years ago, nobody imagined that the cosmos might be blowing up like a balloon. Edwin Hubble didn't expect it when he set out to measure the motions of galaxies in the years after World War I. He didn't anticipate that scientists would spend much of the 20th century trying to understand the expansion he would discover. And no one could guess that the expansion wouldn't be explained until, as we'll see, an even greater scientist made an extremely fruitful mistake. A universe that speeds up as it expands was not what scientists had expected. They began to ask, are we on the right track with all this? Recall that the whole idea of an accelerating universe came out of a project to measure the distances of supernovas billions of light years away. Might there be something wrong with those supernova measurements? It's something the experts are considering with great care. After all, in science, when you come up with a new theory, your first duty is to try and pick holes in it.
So, of course, that's what a skeptic would say, or a healthy person would say, is, well, how do you know that the supernovae that you're seeing 5 billion years into the past are the same as the ones nearby that you're comparing them to get this distance measurement? As far as the properties of the supernova changing, we can take the light from the supernova and spread it out into a spectrum and compare it in detail to the spectra of the supernovae we see right nearby. As far as we can tell, there's no difference in the spectrum. So that's very encouraging, because the spectrum depends on what the chemical composition is, how fast the stuff is moving in the explosion, how hot it is. A lot of details go into making up the spectrum. So if they agree, if the two things look the same, that's an argument anyway that they might be the same kind of object.
All the second guessing about cosmic expansion has a long history. In a way, it started with Albert Einstein nearly 100 years ago. He was the first to introduce a cosmic repulsive force, and he named it cosmological constant. But after a short interval, he was stricken with second thoughts and he threw it out again. The story has become a favorite of cosmologists, one that nearly everybody in the field likes to relate.
Well, the interesting thing, of course, is that the idea that there might be something to balance out the attractive force of gravity with a sort of springy nature of the universe is something that Einstein thought of in 1916. In 1916, his theory of general relativity showed that you could have a universe that was expanding, or you could have a universe that was contracting, but what you could not have was a universe that was static.
There's a wonderful double irony, at least, in Einstein's work on the cosmological constant. Picture him sitting there in the cold winter in Berlin while World War I raged in the trenches, and he was left to his own devices, shunned because he'd been a pacifist in the early days of the war. Einstein sat there in his office and he looked at the equations he'd written down describing the universe, and he was horrified, I guess, to discover that they implied the universe must always be contracting or expanding.
The attractive force of gravity caused the entire universe to collapse. And the way he got around that problem was to imbue empty space, completely empty space, with this repulsive force to counterbalance the inward pull of gravity.
And so he naturally worked on his equations, following the rules of mathematics, until he found that one possible value of this cosmological constant would balance the universe, so it would neither be expanding nor contracting.
But after thinking about it for a while, Einstein realized that his cosmological constant didn't really stabilize the universe after all. In fact, it made the whole thing unstable. At the slightest provocation, the entire cosmos would either collapse under its own weight or blow itself to smithereens. Einstein felt this simply wouldn't do. He was still searching for a way to make a universe that was permanent and unchanging. But if a cosmic repulsion force couldn't do the trick, what could? It was more than puzzling. It was an embarrassment.
And you know, Einstein, oh mein Gott, this is terrible. And he is acknowledged as saying this was the biggest mistake of his life. It would have been the fourth prediction of his general theory of relativity, and probably the most spectacular prediction. But even Einstein couldn't take the leap to say that, to follow the consequences of his theory all the way and say, it predicts the universe should be expanding, by God it should be expanding. He couldn't conceive of that at the time.
In the early years of the 20th century, it just seemed natural to most people to assume that the universe was eternal and unchanging. Not even Einstein could get beyond that assumption. A failure of imagination like that was out of character for the great man. It might have cost him his third Nobel Prize. But at least his bewilderment didn't last long. His conceptual block was shattered in 1929 when Edwin Hubble announced that the universe wasn't stable and unchanging or anything like it. The cosmos was expanding, racing away from a long-ago cataclysm that today we call the Big Bang. The news burst like a bombshell on the scientific community. Einstein, probably with a big sigh of relief, took the cosmological constant out of his equations. Hubble did his work so well that the initially fantastic idea of an expanding universe came to be accepted. In a few short years, most astronomers learned to think of the cosmos as a dynamic place with a dramatic history. Massaging the equations to allow for a stable universe seemed completely pointless.
Many scientists were convinced about 1930 that we really live in an expanding universe and that you don't need the cosmological constant. And I think many people were persuaded, at least by this legend, that it was Einstein's greatest blunder not to touch the cosmological constant again, that it was such a bad idea. It was sort of a theoretical poison ivy and kind of not a good thing to put your hands on. Because after all, if somebody was going to make a case for the cosmological constant, they'd have to be saying, in effect, they're smarter than Einstein, which, you know, may be true, but it's not likely to be true.
Well, when you're a genius, the biggest blunder of your life may actually be, you know, something quite useful to the rest of us. And it looks like the universe does have something like a cosmological constant, and it's what's causing the universe to accelerate.
Despite the prestige of Einstein, or perhaps because of it, the idea of a cosmological repulsive force might have failed to catch on among astronomers. But new observations were about to add persuasive evidence that turned the balance. To gather this evidence, one team of scientists had to travel, quite literally, to the ends of the Earth.
In the very beginning, the universe was so dense that matter and energy were unable to take the forms we know them by today. They were bound up together in some mysterious higher state we can't duplicate in the laboratory. When the universe had been expanding for about 300,000 years, though, the density dropped enough that matter and energy could go their separate ways. There was a sudden flash of light brighter than the surface of the sun, and that light is still out there, pervading every corner of the universe. But the universe has expanded enormously since then, so that radiation has been stretched out, redshifted, and diluted. To see it all today, we have to look in the microwave part of the spectrum. And even then, you need to use a highly sensitive receiver. The first people to do this were Arno Penzias and Robert Wilson back in 1965. They started out looking for the source of microwave noise in the telephone system and got more than they bargained for. In 1978, they were awarded the Nobel Prize for their discovery. The cosmic microwave background radiation is considered the single most compelling piece of evidence for the Big Bang. For most of the 20th century, that's all it was, the afterglow of the flash at the beginning of time. At first glance, the microwave background seems to be a truly featureless glow, completely smooth and uniform in all directions. But scientific theory predicted that if we looked hard enough, we'd see a faint pattern of brighter and darker patches where the glow was hotter or colder by a few millionths of a degree. If we could detect that pattern,
and measure its size, the theory said, we could learn the geometry of space. This, in turn, could tell us the amount of matter and energy in space, and ultimately, the fate of the universe. In the late 20th century, many teams tried to tease this faint signal out of the microwave noise. But it was a difficult measurement. More than 20 years passed before anyone succeeded.
And only with the COBE experiment that launched in 1989, a magnificent NASA mission, were scientists able to finally measure ripples in the microwave background radiation. This was a magnificent discovery that electrified the community when it was first announced in 1990. And then more experiments were developed in the decade of the 90s, and two of the most successful missions were flown just a few years ago, the Maxima and Boomerang experiments, both of which detected the ripples on the scale of approximately 1 degree in the sky. There's no question that they have seen ripples in the sky as predicted by the theorists, which has enormous implications for our ideas of structure in the universe.
So, just how do you measure ripples in the cosmic backdrop? One group, whose experiment was called Boomerang, decided the best approach was to go to Antarctica to fly a balloon. This wasn't as crazy an idea as it may sound.
They hung a radio telescope from a balloon, and it circled the South Pole. And so it had two attributes. One is it had the new generation of detectors, far, far more sensitive than anything in the past.
The other big advance was the move to Antarctica. The microwave telescope was sensitive to frequencies that are absorbed by water vapor in the atmosphere. It's so cold in Antarctica that the air can hold very little moisture, and the balloon lifted the instrument above most of that. To obtain the highest possible accuracy, the microwave detectors needed to take a long exposure while the balloon stayed at a constant altitude. This is where the Antarctic location really paid off. Normally, balloons rise in the daytime as they warm up and fall again in the evening when they cool off. But in the land of the midnight sun, air temperatures can be stable for days on end. So, the Boomerang team was able to take a picture of the microwave sky with an exposure lasting a full 10 days. This was more than 20 times longer than anyone else had achieved. The result was accuracy better than 1 part in a million.
And it led to this amazing result that you can just see in the picture, that the warm spots are separated from each other by on the average of about 1 degree. And it's a very simple theoretical approach says that the mean distance between these big warm patches tells you the curvature of the universe.
The important thing about this picture from the Boomerang experiment is not the particular pattern of blobs and squiggles. It's the size of the pattern. Current cosmological theories predict the spacing between the brighter blobs in this picture. But the theory also says that the pattern might look much larger or smaller if space is curved. What do we mean by the curvature of space? Think of 2 parallel lines. We learn in school that parallel lines will never meet. But strictly speaking, that's true only if space is flat. If space has a bit of what's called positive curvature, those parallel lines will eventually meet up. In a universe with negative curvature, 2 lines would grow farther apart. Either way, the curvature of space has a huge effect on our view of objects in the far distance. It acts like a distorting lens between us and the cosmic background. And yet there seems to be no distortion in the background radiation. Those microwave ripples appear to be exactly the predicted size. That tells us that space is not curved. We live in a flat universe. Parallel lines will remain forever parallel. But there's a problem. The thing that determines the flatness or curvature of space is the amount of energy and matter it contains. Our theories tell us how much stuff there has to be in every cubic light year for space to be as flat as we observe. That's where the trouble comes in. No matter how hard they look, scientists have been unable to find more than 1/3 of that amount. And that's if they include the mysterious dark matter that we know is out there, but just can't see for some reason. There simply doesn't seem to be nearly enough matter in the universe to make space flat.
Now, when we did this sort of work, trying to measure the density of the universe, taking all the galaxies and adding them all up and multiplying by the amount of dark matter and basically taking a census and figuring out what the density was that way, you get about 1/3 of the value that was predicted from theory or that people expected. And for a while, the theorists would give you those thin smiles and they'd say, well, you know, this work is very difficult, and why don't you continue with it a little more, because the correct answer is 1, and you're only getting an answer of 1/3. Go back and do some more. So people did go back and do more, and they kept getting this answer of 1/3.
Now, you can make the universe spatially flat using a sufficient amount of either matter or energy. So if space is flat, and the amount of matter is much too small to account for that, then somewhere in space, there must be a stupendously large source of energy that, up to now, has been completely overlooked.
So I would say by about 1995 or so, people were really kind of worried about this problem, that the theory predicted a value of 1, the observation showed 1/3, and it didn't look like the observations were wrong. They weren't really moving. So some people used the powerful theoretical method of subtraction. And they said, gee, if the total is 1 and all we see is 1/3, there must be 2/3 missing. And people were brave enough to say, well, maybe it's the cosmological constant. At about the same time, this is when the supernova observations were just getting underway. And by 1997 or 8, it was pretty clear that there was a result from the supernova data which suggested acceleration, which could be attributed to this funny stuff that Einstein had thought of back in 1916 for all the wrong reasons, which has the tendency to make the universe expand faster, or that pushes in the opposite direction of gravity. It looks like we're getting the problem right for the first time, or at least we're beginning to see what the problem is for the first time. So I have this sense of, sort of the shutters banging open, and suddenly we get a clear view of what it is we're supposed to be doing. And it's only in the last few years that that's happened. Nevertheless, I have to admit, I really was very uneasy when we got these results. I really felt that having a cosmological constant was somehow, morally bad, and that we just shouldn't have that. But that helps you have skepticism about your own work, which is a good thing. But in the end, you just have to look at the data and see what it tells you, and it certainly hints, well, more than hints, it suggests, well, maybe a little more than that. It seems to be telling us that we live in an accelerating universe.
It wasn't an easy adjustment at first. The scientists are learning to live with the idea of an accelerating universe. At times, though, some of them confessed to feeling a bit like the White Queen, who boasted that with practice, she had learned to believe as many as 6 impossible things before breakfast.
Dark energy, or the cosmological constant, whatever you choose to call it, it's weird stuff.
And even the experts feel challenged to get their minds around it. The accelerating universe takes some getting used to.
It's still too early to rule anything out definitively. But the key point is that unlike cosmology of a decade or two ago, when it was very hard to make new experiments that could resolve these issues, now it is possible. And all we need to do is wait a little longer with ever better equipment and better techniques, and this matter will be resolved. And I would predict, and I think here I'm in the majority with most astronomers, that based on these new findings, dark energy is here to stay. We have to get used to it.
The physicists had ideas about what the dark matter could be, various exotic particles. The physicists are largely stumped on dark energy. It's some weird field, energy that evidently dominates the whole darn universe, that doesn't cluster, doesn't fall into galaxies, just a smooth stuff that provides pressure that, you know, is pushing the universe out. It's just bizarre.
And the universe has begun to speed up its expansion, and this presumably has not happened since the very beginning of the universe, when the inflationary episode occurred. And now it's beginning again. And if anybody can tell you that they understand why this is happening, don't believe them for a moment, because we are clueless as to why the universe should be so complicated as to contain all these Baroque components.
There's nothing like cosmology to make you feel humble. The universe is so large, and our place in it so small, our understanding so limited. The cosmos abounds with mysteries, yet the clues to solve them are out there, too. The thrill of discovery awaits us around every corner.
The dark energy is a complete surprise. First of all, it's spread uniformly through the universe, so it has no particular effect on stars. It's just a property of space. It's a property of the vacuum. It's like saying, forget about the rest of the universe. Forget about all the stuff you know about the universe. The dominant stuff in it, by a small margin, because they're nearly equal, but the dominant stuff is just a property of space itself. And that's really weird, because we can't create it, we can't measure it in other ways. There's no laboratory evidence for a non-zero energy for the vacuum. Yet this is what we're saying, that empty space has a non-zero energy.
My own view is that we have a lot more work to do, because we don't know what the 1/3 is, the dark matter. Nobody really knows what that stuff is. And we don't know what this dark energy is either.
And we've piled strangeness upon strangeness and may yet go on doing so. And at one deep level, I would argue that that's no argument against something being true or not. In other words, how strange it appears to us is no measure of anything except that we're in a special situation in the universe.
Cosmologists from around the world are already planning a new generation of powerful instruments to probe the far reaches of space. In addition to testing the accelerating universe model, they want to look back to the era when the first stars lit up 11 or 12 billion years ago. They want to witness the birth of galaxies. And there's simply no telling where that quest will lead. The universe delights in surprising us. It may yet turn this whole story on its head. Perhaps to the next generation, the Big Bang will seem as quaint and unreal as the Earth-centered universe of the Middle Ages.
Well, people often ask, what use is this cosmological information? After all, we're here. It doesn't matter what the future of the universe is 100 billion years from now, any more than it really matters how we came to be here over the past 10 or 15 billion years. And to someone who truly holds this view, there is no good answer, and cosmology becomes sort of a plaything of the other people. But for those of us who are engaged in it, of course, it's impossible to avoid the belief that cosmology is good for the soul, that it cheers us up as inquisitive beings to know something about our origins and our possible futures. It's fun to think there are people who are working night and day to try to supply the answers to these questions.
So, that's our picture of the cosmos as far as it's understood at the beginning of the 21st century. If you ever get the feeling that not only is your whole world coming apart at the seams, but it's unraveling faster all the time, well, at least you're not alone. If the cosmologists have got the big picture correct, it's happening to the whole universe and will only get worse. So, we should enjoy the place while we can before time and space go rushing off in all directions.